Conversions that utilize a single conversion factor are very useful, and you can do most of the problems in this course using single-step conversion factors. But it's also useful to think of a process as a whole, which likely requires we string multiple conversion factors together to get us from point A to point B. For instance, if we want to move from a count of particles to the mass of that same sample, we would end up with a big gap in between. This is because we don't have a single conversion factor that includes the unit, such as the atom or the molecule, and a mass, such as grams. However, we do have a conversion factor that gets us from that unit to the mole, and then a second conversion factor that gets us from the mole to the gram. And if we use those two in tandem, we have a seamless process that gets us from point A to point B. In terms of our math, we would move from the unit to the mole by dividing by Avogadro's number. We then move from the mole to the gram using the molar mass of our compound. If it was true that a single conversion factor could be used multiple ways, then it's also true that multiple conversion factors will allow us to go in multiple directions. If I had the mass of a sample and I needed to work towards the unit, I could divide the given mass by the molar mass and then multiply that by Avogadro's number. You really shouldn't work to memorize a series of steps here. The more conversion factors we add to a scenario, the more complicated it gets. Instead, work to understand why you are using a conversion factor in a particular scenario. This will translate a whole lot better from one problem to another than just memorizing a series of steps. Now, on to our problem. Here we are given mass and we're asked for molecules. The path to get from our given quantity to our wanted quantity has to involve more than one step since we don't have a conversion factor with both grams and molecules in it. We're going to follow the path we laid out earlier. Like the single-step problems, start with your given quantity. I've abbreviated caffeine CAF so it won't be quite as long to write. This allows me to keep track of what I have, but it saves a little bit of effort. To move away from the mass into the mole grouping, I need to divide by the molar mass so that the grams units can cancel. Next, to move away from the moles, we need to multiply by Avogadro's number. We should now be in terms of the unit molecules, which is appropriate for our sample. To solve your equation, everything in the numerator will get multiplied together. Everything in the denominator will separately get multiplied together. And then the numerator will be divided by the denominator. You can also enter 1.54 divided by 194.22 and then multiply that result by 6.022 times 10 to the 23rd. As long as you are using the exponent button for Avogadro's number, you should come up with the correct answer. We can place as many steps in our train track as are necessary to complete our calculation. Maybe you need to string 23 conversion factors together. Cool, you'll just have a really long train track. Luckily, our tracks won't ever get quite that long, but there might be times that you need to include 5 or 6 steps to complete a problem. This problem requires that we tack on a step from the last one that we did, as we are asked to move from the number of formula units to the total number of ions. Since we are given grams of our compound, this one is going to start very much like the last one. Use the molar mass to move away from grams and towards the mole. Avogadro's number will help you move towards the formula units from that mole. Because we are asked for total ions, we have to add our extra step here. We know that there are 3 ions for every 1 formula unit of calcium chloride. Once you multiply everything in the numerator together and divide that by everything in the denominator multiplied together, you'll have a value for the number of ions present in this sample.